Thanks, Ime. So I'm actually excited to introduce our colleague, Professor Animashree Anandkumar, as our keynote speaker for the workshop. Thanks, Anima, for joining. Anima is currently a Bren Professor at Caltech, where she co-leads the AI for Science initiative, among other leadership roles. She's also a Director of Machine Learning Research at NVIDIA, so she's wearing multiple hats. And she has made several core technical contributions in machine learning and AI, and particularly has spearheaded the development of tensor algorithms, which is now getting used everywhere in AI applications. Please join me in welcoming Anima as the keynote speaker.
Hi, everyone. Great to be here, and apologies for the earlier mix-up. It's always a bit challenging when it's early, and thank you for understanding, and thank you for being here, and thank you, Arindam, for organizing this. So yeah, let me share the screen. Give me 1 second. I think yeah, just give me 1 second. It should work. Yeah. Did you see, or?
We are seeing your Slack.
Oh, why did it go to Slack? I think I pressed I thought I did oh, I did yeah, this is better. Sorry about that. Great. So I want to, give an overview of our recent work on learning neural operators for solving PDEs, and more generally, right, how to capture complex phenomena we see that are highly multi-scale and possibly chaotic. So how do we handle these systems at scale? And it is no exaggeration that differential equations are considered one of the most powerful tools humanity has ever created, right? Everything from fluid flow to modeling material properties, looking at seismology, right? The activities of the earth. All these require highly multi-scale phenomena that can be captured by partial differential equations. So what makes it challenging for traditional methods to solve is the inability to generalize, right? So, it's doing brute force numerical calculations and doing it also at multiple scales. You can't solve this complex problem all at once. You have to do finer scale calculations and be able to exchange that with coarser scale calculations. And this constant exchange is very expensive and requires supercomputers for some of the most challenging cases. And so the question is, can we use the power of machine learning to speed this up? And how we can possibly speed this up is to think about generalization, right? So if you've already solved problems, let's say with some set of initial conditions or boundary conditions for a family of fluid flows, there should be similar related solutions for similar, or at least, in a way, related solutions for others in the same family, right? So there is certainly what we know is ultimately the solution operator, right? So this is the represents the solution for any finite dimensional discretization of your inputs, right? If you can learn that efficiently, then you can solve this any equation in this family effectively. And so the question is, how do we learn that well? And so that's why we call it neural operator learning. Can we learn this solution operator in a tractable way and with guarantees? And this is an interdisciplinary work, having people from applied math, material sciences, and that's what kind of informs us in terms of what traditional methods are doing and how we can obtain, right, inspiration from that to design tractable and guaranteed AI methods. Yeah, so the way we want to set this up is the input can be a set of coefficients, which are initial conditions and boundary conditions, right? And from that, you want to be able to predict the solution. And so the main difference from many other works that look at learning on PDEs is that those works focus on learning one instance of the problem. So meaning you're kind of given one fixed initial and boundary condition, you want to learn the solution. But the problem is, this is only useful if you're using just that exact setting many, many times, right? Then the neural network can have a good speed up. But on the other hand, if you need to be able to change the conditions and try this on a new one, you would have to retrain the model. So that's not very effective. So what we instead need is one that can directly be able to give you the solution for any initial or boundary condition. And so the main aspect that I mentioned that is different from traditional neural networks is this ability to have infinite dimensional mappings, right? So, or continuous mappings. So for standard neural networks, the inputs and outputs are finite dimensional. Could be image, could be text, right? So, I mean, the text could be variable length, but still the vocabulary is fixed and finite. On the other hand, if you think about solving partial differential equations, right, ultimately you would need the solution at any arbitrary resolution, right, any arbitrary point in the domain, and the domains themselves could be arbitrarily shaped. So how do we learn this mapping between potentially infinite dimensional spaces? And that's what is an operator, right? It maps function to function. So that aspect, how do we incorporate that in learning neural networks? So I think the way we do this as building blocks is similar to how we think of the standard neural networks. In a standard neural network, you have some fixed dimensional input and you want to output against, right, in some fixed dimension. Let's say in the classification problem, it's some label that you want to output. And what you have is some linear function and composing it with nonlinearity. And what we want to extend this to is infinite dimensional mapping. So where the input would be some infinite dimensional function, and the output could also be potentially infinite dimensional. So how do we capture that and still get a universal approximator for learning operators? And that's what we call the neural operator. And the main building block here for the linear layer is what we call the integral operator. And so the inspiration of this comes from solving linear PDEs, right? So if it's a linear PDEs, we already know the structure of it is in the form of integration with the Green's function or a kernel. So this kernel represents the Green's function, and this is a continuous convolution operation. And through that, you can obtain solution for equations such as, say, the heat diffusion equations. So we know the structure of the equations in those settings. And so now the way we want to formulate it is to start with that integral operator, compose it with nonlinearity. And by doing that, we can now capture any nonlinear PDEs, right? So that's the outcome in terms of getting inspiration on how to solve linear PDEs and using that as a building block by composing it with nonlinearity together to come up with universal approximation for any operator. So now, theoretically, you should be able to solve any nonlinear PDE and learn that using this neural operator framework. So that's the foundation, right? So we've now been able to extend the notion of universal approximation for finite dimensional neural networks to ones that are potentially in infinite dimensions, and still be able to have the notion of linear operator here. right? So this is now integration over a continuous domain, but this is continuous integration, right? But by composing it with nonlinearity, we can get any general approximation. So this is a general framework, and indeed we can prove that similar to the counterpart, what we have with finite dimensional neural networks, that it can universally approximate any continuous operator. And so now for, in fact, for very well-known families of equations, say like the Navier-Stokes, right? So that is for fluid flow. We know that the solution operator lives in finite dimension, right? So even though it's mapping between infinite dimensional spaces, the solution operator itself is of low dimension. And so given that information, we would expect also the neural operator to have a small number of parameters. And that's how you can prove that the number of parameters of such a neural network would not be too high. So this is giving now some finite approximation bounds when the solution operator is also of finite dimension. And so that's the main aspect here, right? There is no magic. If everything was infinite dimensional, there is no way we could get a good approximation using only finite dimensional neural networks of finite size. Instead, what we have is solution operators that in many of these popular families are finite dimensional or low dimensional. Hence, we can expect efficient learning here. And that's the overall framework that, as a conceptual one, what we want to build are nonlinear compositions of integral operators, or these operators, right, that look at integration with the kernel. And if we can learn what this kernel integration is, then we can, compose it with nonlinearity and get a solution in the end. So now the question is, how do we still solve this efficiently, right? This is now a continuous operator, right? So this is also hard to solve if you are only given finite inputs. So you're given inputs of different discretizations, or even different samples, say even of the same discretization. You have to go from those discretizations to this continuous domain. So how do you do that? How do you get a good approximation of this kernel integration? And that's where we tried several variations. Natural aspect is to think about graphs, right, to do this kernel integration, because you can think of nearest neighbor kind of graphs that look at discretizations, discrete approximations of this continuous integral. But the one that worked really well in our setting is called the Fourier neural operator, where we use the Fourier transform to solve this convolution efficiently. So if you remember, so that's kind of the, the first I wanted to bring this up. If you remember your signal processing 101, right, the convolution in the standard domain becomes multiplication in the Fourier domain, right? So if you assume this kernel is translation invariant, which is a reasonable assumption to make in many of these situations, right? So what we would get is this convolution is nothing but a multiplication, element-wise multiplication in the Fourier domain. And so learning this kernel for convolution is equivalent to learning a weighting matrix for the Fourier transform of your input. And so with this in mind, what we think of now, this convolution operator, is one that takes the Fourier transform of your input and then filters in the Fourier domain and does the inverse Fourier transform. So what we also add in addition is an inductive bias, where we pick only the low frequency mode of this, of the input Fourier transform. And the intuition is by picking the low frequency modes, we can invert it in a stable way. And because of nonlinearity, you can still get overall in the end, the high frequency modes, right? You don't have to solve for that in one layer of this network. And so that's a good regularization to enable learning well. And the reason we pick Fourier transform is what we want is to be able to capture global correlations. Whereas if you only have your standard convolutional neural network, it captures only local information, right? So, like edges. But in fluid flow, there is highly global correlation, both in space and time, right? So like currents here would have an impact all the way over here and all the way forward in time. So you cannot just use small window convolutions to be able to capture that. So that's the reason standard networks like UNets do not usually work well if you are trying to learn this from scratch. If you have to solve for this from scratch, they won't be able to capture this global phenomenon very well. And so what we see is this is the first machine learning method to be able to solve Navier-Stokes very efficiently and be 1,000 times faster compared to traditional methods. And also the benefit of having this resolution-free training is that you can afford to train just on low resolution and directly get this zero-shot super resolution. So the idea is we can capture this rich information through operator learning. And indeed, the training resolution cannot be arbitrarily small, right? So you need at least some minimum level of resolution to capture the underlying solution operator. But once you capture that, you don't need higher resolution training data. And that's kind of what makes this work very well. And so you also have cheap training. You don't have to get expensive training data. And so that's the benefit of this method. And we also compared it with other machine learning methods, which only work on the same resolution. They cannot generalize to higher resolutions beyond. And so that's, and even there, we see our method getting to a much better error, right? So the idea is by being able to generalize to other resolutions, you also learn well to generalize in the same resolution. And be also able to capture the higher frequency spectrum. So what we see is, again, if you use the Sobolev norm, the H2 norm, you're also fitting to derivatives up to second order, and that captures the spectrum much more effectively compared to just the L2 norm. And these are much more effective compared to UNet and other standard neural networks. And so that's the idea, being able to capture also this high frequencies, and that's how you can be able to resolve these higher resolution inputs. So with this, we can solve inverse problems very well, because what they require is a lot of forward evaluations. And so we can get a good speed up there. Many other applications of this, we've had the plasticity, which requires multi-scale, simulations. And there the speed up is even higher because the standard packages are on CPU, and there's a lot of room you also get by moving on to GPUs and with neural networks. So you get the double benefits together here. And in ultrasound simulation, what we need is the ability to simulate how it travels through the body and the organs, and be able to capture both the wavefront and diffraction very well here. Like carbon dioxide, being able to handle that is a pressing problem of our times, right? So being able to model the gas saturation and pressure over the next 30 years is so critical. And what we've seen is very promising results in this regard. And so the other aspect is to also be able to capture both the physical constraints along with data-driven methods, the physical constraints being the equation loss itself, right? So can we fit to this equation loss? And what we see is this ability to, if you're training a PIN model, that is, you're using only the equation constraint and no data and no pre-training, it is, especially in the challenging regime of trying to predict for a longer time interval, we see that training from scratch doesn't get to the same error as being able to, first have the pre-trained model over the set of equations, set of data, and be able to fine-tune on a given test instance. And we see that as well, being able to generalize, from one Reynolds number to another, being able to do that in the turbulent regime well. So I don't want to go into this more because I want to leave a few minutes for questions, but the idea is we can also capture invariant statistics, say in chaotic systems where you cannot hope to predict long-term behavior, but what we show is being able to capture the invariant statistics well. Yeah, so to conclude here, what we showed is the neural operator being able to frame this as learning the solution operator itself. So there is no dependence on a resolution or grid. And the Fourier basis helps us solve this continuous integration and approximate it in a good way, in an efficient way. And so being able to compose that over several layers gives us the ability to approximate any nonlinear PDEs and be able to generalize very efficiently. Thank you.
Thanks, Anima. This was great talk. We have quite a few questions. Before we get to the questions, quick announcement. So poster session starts at 12:30 Central Time. This is going to be on ML and climate. So keep that in mind. So let's get to the questions. Maybe we have time for a couple of questions. So one question is, somebody wrote that I'm very confused about how the convolution, which is linear, that is first power of V, can be applied to nonlinear problem. Can you clarify?
Yeah, that was the whole aspect here, that it is composed with nonlinearities like ReLU or something else. So yes, each layer is linear, but overall it's composed with nonlinearity. So that's why it can be a general universal approximator, same as in a finite neural network, right? So you have matrix multiplication, which is linear, and you compose that with ReLU or some nonlinearity.
Okay. Another question is, do you implement convolution operation in Fourier transform form? If so, what are the benefits of it? Can we use similar idea in computer vision domain?
Yeah, so the main benefit is the ability to capture more global correlations, which is very crucial for these applications. And we know that, the aspect of learning the solution operator well is being able to capture the frequency spectrum well, right? So if by operating in the Fourier domain, we can step by step do that. I mean, we don't claim in one layer you can't capture the whole Fourier spectrum because we are filtering to just low frequency modes. But by using nonlinearity and composing it over several layers, we can get a good approximation.
Okay, so we are getting a lot of questions in Slido, so maybe we have time for one more. So the FNO is elegant. Can it be used to learn randomly located forcing terms, that is, learn a PDE that works for any emission sources without retraining?
Yeah, I mean, so this is a purely data-driven method, right? We don't even need to assume the equation structure in any way. So it can capture any kind of complex phenomena, especially those that are not limited to one grid or one resolution or highly multi-scale. Those would be great use cases.
Okay, so I think we'll wrap up, but Anima, if you can, I have a quick question, if you can quickly answer. So Fourier is one of the folks' favorites, orthonormal basis that we transform things to, but there was a phase in ML and signal processing where people were looking at dictionary learning, where even that basis was being learned from the data. I don't know if you guys have looked at that or considered that, or Fourier does seem like something fundamentally better.
Yeah, I mean, the main challenge is to be able to learn something global, right? So the, convolution neural network learns it locally small once, and it's too many parameters if you try to learn it globally. And so that's why the Fourier is a good inductive bias.
Makes sense. Thanks so much. Thanks, Anima, for the talk, and thanks everybody for joining.